Okay, we have just located the bright spots and dark spots of a two-slit interference pattern, otherwise known as the Young's experiment. But now we want to go one step further. What I want to know is not only the location of bright and dark spots, but exactly what kind of function this is, the intensity function. Okay, the intensity function. For example, what is the intensity at that point? It's neither totally bright nor totally dark. How much is that equal to? Okay, I want to know intensity is a function of y. Okay, the distance on the screen. How do we do that? Well, first of all, intensity goes like electric field squared. Okay, so we can find the electric field. The electric field add up according to the superposition principle. You have to add E1 and E2 up. Okay, and you add them up, and then you find the total electric field, which is E1 plus E2, and then you have to square it, find the time average value of the squared, you get intensity. Okay, so that's the idea. So now, here, E1 is the electric field produced by light coming from the first slit. Okay, and when it arrives at the location of the point of interest on screen, it is equal to E1 times sine omega t. And E2, on the other hand, assuming for simplicity it's got the same amplitude, E0, same frequency of course, but it's got a phase difference, phi. Okay, it's got a phase difference, phi. Or more precisely, we call it delta phi. We have to add these two electric fields up, E1 plus E2. So we have to deal with the addition of two sine functions. Okay, and what if there are 3 slits or 4 slits? Then you have E1 plus E2 plus E3 plus E4. You got to deal with 3 or 4 sine functions added together, right? But these sine functions, they have something in common. What do they have in common? They have the same exact omega. Okay, now where did we learn a particularly good method to add different sine and cosine functions together if they have the same angular frequency omega? Okay, we learned that before in a previous chapter when we studied what? AC circuits. Remember that? And buzzword was what? The key concept, phasor. What's a phasor? It's an artificially defined vector, okay, such that its y component represents the actual physical quantity, which in the previous case was current or voltage. In our case, it's going to be the electric field produced by a certain source. And since the actual electric field varies with an angular frequency omega, this phasor will then turn about a fixed point here at the same angular speed omega. Okay, when you add different phasors up, since each phasor has the same exact angular speed, they're going to turn with the same exact rate. So the net vector, the resultant vector, also turns at the same angular speed omega, which means the entire structure turns rigidly together. Okay, now what I'm looking for is E1 plus E2. If I think of E1 as the y component of a phasor and E2 as the y component of another phasor, so we have phasor E1 and phasor E2. If I add them together to get E, then isn't it true that the y component of the resultant phasor is equal to this y component plus that y component? In other words, E equals E1 plus E2. So what really is the summation of these two electric fields? It in fact is the y component of the resultant phasor. Alright? The y component resultant phasor. And what determines the brightness, of course, is the amplitude of the electric field E, which is E1 plus E2, which is in our case the amplitude, the length of the resultant phasor. Okay, so instead of trying to add these sine functions together, which you can do, but it's cumbersome, what we're going to do is we're going to draw a vector phasor representing each source. So in our case, we're going to draw 2 phasors, one for source 1, one for source 2. Then I'm going to draw the resultant phasor, okay, and the amplitude of this resultant phasor will tell me how strong the resultant electric field is. If you square that, you will get the intensity. Let's see how this can be done. Okay, the first phasor has an amplitude of E0 right here and makes an angle omega t with a reference line. Therefore, the y component is the actual E1, which is E0, the amplitude times what? Sine omega t, right? Sine omega t right here. The second phasor has the same length, E0, but it makes an angle of omega t plus delta phi, with the same reference line. So the actual E2 would be E naught times sine of omega t plus delta phi, which is right here. Okay, now I'm going to add them together now. This is how I do that. Okay, I'm adding two phasors together, tip to toe. Here's the first phasor, here's the second phasor. Now recall that these two phasors differ by a phase angle of delta phi. Okay, look, the second phasor leads the first phasor by a phase difference of delta phi. So here's the first phasor pointing this way. The second phasor I have to turn that way by an angle delta phi. Okay? Now, assuming they have the same magnitude, E naught and E naught, what you get here, the resultant E will form an associated triangle with E1 and E2 because these two lengths are both E naught. Okay, what I'm looking for is the amplitude or the magnitude of the resultant E phasor. Okay, of the resultant E phasor. Can you see it from this diagram? Well, it's quite easy to see. If I were to drop a perpendicular, then I'm cutting this triangle in half. Okay, cutting the base in half. How much is this angle? This angle equals that angle because it's isosceles, and when you add them together you get delta phi, don't you? So each angle really is delta phi over 2. Okay, so is that. So how long is it from here to there? This is a right angle triangle, so you get E naught here, and this angle is delta phi over 2. Therefore, the length between here and there would be what? Delta phi over cosine delta phi over 2 times what? E naught. And you double it. Because there are two of them, you get what? You get E. The amplitude of the resultant phasor. Okay? The amplitude of the resultant phasor. And the intensity that you see on screen is directly proportional to E squared. Okay, to E squared. So I is proportional to E squared. Alright, let's square it. So when you square it, what do you get? You get 4 E naught squared. And then cosine squared delta phi over 2. Okay, so I is proportional to that. Now forget about the 4 E naught squared. This is just a constant. And it's not the same constant that will give you I. If you want to go from E squared to I, you have to add yet another constant. So overall, I would say, equals some constant I naught, which depends on E naught squared, depends on speed of light, whatever other things, and then cosine squared delta phi over 2. Right? Now, what is delta phi anyway? In our case, delta phi is the phase difference between these two phasors, and the phase difference. Here's how we find the phase difference. Okay, here's how we find the phase difference. The phase difference delta phi equals k delta x. Do you buy that? Because the first phase is kx1 minus omega t. The second phase is kx2 minus omega t. Same k, okay? Same k. So the difference would be k times x2 minus x1, which is k delta x, right? K delta x. Okay, now I know what delta x equals to. In my case, I already know what delta x equals to. All right? Delta x equals to, going back to the previous case, d times y over L. Okay, or d sine theta. I can write d sine theta instead. That is delta x. That is delta phi. Plug that delta phi expression in, then I get I equals I naught cosine squared k d sine theta over 2. The only thing I have left to do is to determine what I naught is equal to. Okay? Determine what I naught is equal to. Now, one typical way I can do it is to use a reference point on the screen, using the intensity at that point as a reference. Look at what happens to the cosine function. This cosine square function, we know any cosine square function, the maximum possible value equals 1, right? And what does that happen? That happens when the argument equals what? A multiple of pi. In particular, what happens at the center of the screen? At the center of the screen, theta equals 0, sine theta is also equal to 0, and therefore, the whole argument, the whole phase angle becomes 0. Cosine 0 is a maximum, which is equal to 1. So, when you set theta equal to 0, the cosine squared function becomes 1, I equals I naught. So what is I naught really? I naught is the intensity in the middle of the screen. Okay, it is also the maximum intensity. All right, it is also the maximum intensity. So that's what I naught really means here. And this formula is one step further than what we did before because it tells us the intensity at every location on screen. Okay, every location on screen. In particular, how do you get a bright spot? You get a bright spot, okay, when the cosine function cosine squared becomes what? Becomes 1, right? So this whole phase angle, okay, this phase angle. So if the phase angle KD sine theta over 2 equals to a multiple of pi, okay, n pi, right? Then of course, you got cosine n pi, which is plus or minus 1. You square it, you get 1, okay? So that is the condition for bright spot. Do we get the same answer as we got before? Well, let's see here. What is sine theta anyway? Sine theta is equal to y over L. Okay, take a look. Sine theta, this is sine theta equals y over L. Am I right? Okay, y over L. So k is 2 pi over lambda, of course. So 2 pi over lambda times d divided by 2. Don't forget there's a 2 here. And then y over L. That equals n pi. That is the condition for bright spot according to this expression. Does that agree with what we got before? Well, let's check. Okay, there's a 2 pi here, so that 2 cancels, pi cancels, right? And then you have what? You solve for y. You find y equals to L lambda over d times n. That will be the condition for bright spot. Is that the same as we got before? Well, let's see here. That's the result we got before. L lambda over d times n. You see that? Exactly the same. Okay, of course, again, this is better because this tells us the intensity in every location, not just where the bright is, where the dark is. Okay, you can, for example, plug in theta equal to 30 degrees and look at what is the intensity looking 30 degrees away from the reference line. What is the intensity you can calculate from this function? Okay, and in general, when you plot this cosine squared function, you're going to get something like this. Okay, as a function of sine theta, you are going to get something like this. Okay, so as you look at the intensity distribution on the screen, you're going to see a broad bright peak, and there's a 0 here, and there's another broad bright peak, and so on. Okay, so the bright peaks are quite broad, and they're not all that sharp. Okay, they're not all that sharp. It's pretty broad here, pretty broad here, pretty broad here, and here is dark, dark, and dark. Okay, and overall it's a cosine squared function. That's something good to know. Okay, with the idea of phasors in mind, we're not limited just to Young's double slit. We can look at a triple slit example, a 3-slit example. All we have to do really is to add 3 phasors up, right? Because each slit is a source, and it gives us a phasor. So we have to add 3 phasors up. For simplicity, let's say these 3 phasors, these 3 beams are projected onto something very, very far, so they're almost parallel to each other. Okay, so the screen is very, very far, and this angle is theta. This angle is theta. So is this angle. So is this angle. What I want to know is the intensity on the screen as a function of theta. Okay, now let's make a little twist. Let's assume that the amplitude going through the middle slit is twice as much as the amplitude going through S1 and going through S3, just to make things a little bit more interesting. Okay, so we don't have equal brightness coming out of each slit. The one in the middle gives us twice the amplitude. Okay, twice the amplitude. How do I find the intensity on a distant screen as a function of theta? Well, again, let me draw a phasor for each of them. Here is our first phasor, E1, making angle omega t with reference line. Okay, now if this is E1, what about E2? E2, you have to take E1, okay, you have to take the direction of E1, and then you have to turn a little because there's a phase difference. There's a phase difference. What's the phase difference? This angle is theta. The phase difference, delta phi, would be k, if this is d, okay, if this is d, would be k times d times sine theta, right? K times d times sine theta, because d sine theta is delta x. Okay, d sine theta is delta x, so it's k times delta x, which is k d sine theta. So anyhow, the phase difference between x1 and s2 would be k d sine theta. That's delta phi. The same phase difference exists between s2 and s3. Okay, because that's the same distance d, right? So this is also same delta x. So this is again S3 is ahead of S2 by a phase angle of k d sine theta. All right. So how do I draw the second phasor representing S2, representing the electric field coming from S2? It will be starting from this thing, and it's gonna go that way. It's gonna go that way, twice as long. Okay, twice as long, because we know E2 is twice as long as E1. So this is E1, E2 is twice as long, and this phase angle is delta phi. Okay, delta phi is right here, k d sine theta. That brings us to the third phasor. How do you go with the third phasor? With the third phasor, you have to take the second phasor, this reference direction, and you're going to turn another delta phi. Okay, another delta phi. So, and it's got the same length as E1, so it goes that way. Okay, it goes that way. That is E3. So this is E2, and this is E3. This is E3. Okay, E1, E3 have the same length, and E2 is twice as long. This angle is also delta phi. Okay, what is the resultant phasor? Well, the resultant phasor simply starts from first one, ends with the last one. So you simply connect them together. Okay, connect these two points together. This is the resultant phasor, E. Okay, the geometry is quite symmetrical. So that makes our job easier. You drop a line like this, perpendicular like this, drop a perpendicular like this. Now look at the symmetry here. You break this into E into three parts. 1, 2, 3. Okay. How much is this? Well, this angle is the same as delta phi, right? So this delta phi. So how long is this between here and there? That would be E1 times what? Cosine delta phi. Okay. So you get the first one. E1 cosine delta phi. That's from here to there. And then you add between here and there. That's the same as the length E2. They're parallel. Okay, they're parallel. E2 is twice as much as E1, so I just add 2E1. Okay, add 2E1. And then what about between here and there? Well, this length is also E1, just like that. And there's another cosine phi, cosine delta phi, right? Because this is also delta phi. So you just add another term. E1 cosine delta phi. Same thing. 1, 2, 3. Add them all together. That is E. That is the amplitude of the resultant phasor. Okay, the amplitude of the resultant phasor. Now let me clean this up a little bit. I'm going to take that E1 out. I'm going to take that E1 out. In fact, you combine these two terms together, it's 2E1, and then times what? Then 1 plus cosine delta phi. Okay, this is the resultant electric field amplitude. Now, what about the intensity of the three-slit example? Because we can only see intensity. We do not see the electric field directly. The intensity goes like amplitude squared, E squared. So it's got to be proportional to 1 plus cosine delta phi squared. Right? It's got to be proportional to that. But there's a constant in front of it. I want to know what that constant is. Okay, let's call that constant C. Then I have I equals C 1 plus cosine delta phi squared. I have to know what C is. And again, the way we find that constant is by using that one reference point. One reference point. It sometimes is at the center of the screen, and sometimes you can simply use the brightest intensity, the maximum intensity, as a reference. Okay, clearly the maximum intensity occurs when cosine delta phi equals what? Equals 1, right? So then 1 plus 1, that's 2. 2 squared is 4. Okay, and then when is cosine delta phi equal to 1? It happens when this delta phi equals what? 0 or 2 pi or 4 pi, whatever, right? And in particular, this can be realized at the center of the screen where theta equals 0. When theta equals 0, delta phi is also equal to 0, so you have a brightness. Let's say the intensity at that point, when theta equals 0, we call it I naught. Okay? At theta equal to 0, I equals I naught. That's how I define I naught. But wait a second, I naught also equals to this expression, all you have to do is plug in theta equal to 0. Now when theta equals 0, again delta phi equals 0, cosine theta phi equals 1. 1 plus 1, that's 2. 2 squared, that's 4. It's 4 times c. Right? So what did that tell you about c? C is 1/4 of I naught. So finally, I have I equals 1/4 I naught times 1 plus cosine delta phi. What's delta phi again? Let's plug that in. K d sine theta squared. Okay, this is the expression of a 3-slit interference pattern. This is the intensity as a function of the angle theta. If the middle slit offers twice as much amplitude of its electric field as the other two, right? Of course, you know, if you understand the general idea of phasor addition, that I can make any twists and turns. You can always finish it accordingly. For example, I can say, oh no, what if these two d's are not the same? Okay, and if these two d's are not the same, of course the delta phi's are not the same, right? So this angle and that angle will be different, right? So it will make the calculation a little bit longer, but the idea is always the same. You still add these three phasors together, except the resultant line is not going to be parallel to E2 anymore. That's all. Okay, so with phasor diagram, you can find an n-slit interference pattern simply by adding all these n phasors together. You can always do that. Okay, so what's next in this chapter? Well, we're going to study other examples of interference. As we stressed before, to cause interference of visible light, you must take the same source and split it apart. Okay, same source split apart. It's no way to put two different sources together and expect them to be coherent to each other. And there are different ways to split the source together. What we learned here is to take the same beam and simply by opening tiny slits belonging to the same wavelengths. This is only one way to split the same beam. Okay, we can also split beams by reflection. You know, we can allow a mirror to reflect a beam to combine with the original beam. Okay, and we have other different ways to do that. So in the next part of the lecture, what we're going to do is we're going to look at other ways to split a beam. Okay, you must take a beam and split multiple ways and add them together, back together to cause an interference pattern, and you will see other examples of interference.